Quality and Performance Part 2. In the previous part, we talked about cost associated with quality. We talked about some history of quality management, some approaches to quality management such as TQM and Six Sigma, and we finally ended with acceptance sampling. We also saw that acceptance sampling has some disadvantages. When defect rates are very low, you must sample a large amount to detect defects. Also, it's more suited to batch processing where you have batches of production and you sample them. It's not as, it can obviously be applied to assembly lines as well. You sample every 1,000th piece or every 100 piece coming off the line. But the main disadvantage is that its cost goes up as your defect rate goes down because you must sample a bigger and bigger amount to find the defects. In part 2 now, we're going to discuss an alternative approach to capacity management called statistical process control and its associated ideas of process capability. These ideas were first developed in World War II and have become immensely popular and useful, and in most manufacturing setups, you'll see some version of statistical process charts being used in some areas. So today we're going to talk about process variation. We saw last time that variation can increase defects, especially when we talked about Six Sigma. We discussed this idea. We're then going to talk about process capability first, and then statistical process control. A lot of textbooks will cover process control first and then talk about process capability. I think that's a little bit backwards, because if a process is not capable, there's no point in trying to control it, because control means you are trying to make sure the process stays its course. It does not change. If it's doing good, it continues to do good, right? It continues to do what it's doing. But with just simple process control, you're not guaranteed that it's doing good in the first place. So it will continue to do what it's doing, but if it's not doing something good in the first place, it will continue to do something not useful. Process capability ensures that the process can actually meet customer specs, so it's useful to begin with. And then once you establish that a process's output is going to be useful, it's going to meet customer specifications through process capability calculations, then it makes sense to control this process, because it is meeting customer specs and you want it to continue to meet customer specs. Okay, so that is why I believe the more logical order is to study process capability and then study statistical process control, right? It's kind of like when you study lean methodology, you learn that one of the most useless things to do is to optimize that which should not be done in the first place. Same idea here. It's useless to control a process which does not meet customer specs to begin with. It's just not capable. So there's only economic advantage in controlling capable processes. If the process is not capable, you have to redesign the process. There's no point trying to control it. Let's get an idea about process variation. And the idea of process variation underlies all of what we're going to do next. Students often find statistical process control and process capability to be difficult concepts. This is because most textbooks, or many textbooks, will get into these ideas without initially clarifying what process variation is and what is the model of process variation that these calculations are based upon. So we are going to spend some time studying process variation, looking at some examples, so we understand, then if you understand that, the process variation part, the remaining parts will become very easy for you, and you'll easily see, okay, what's process capability getting at and what is statistical process control getting at. Deming said that a bad system will beat a good person every time. Part of the training in quality that Deming would give to managers and large corporations was to show them the importance of improving systems and not just focusing on people. If you are coming from an HR organizational behavior background, you might have studied the importance of people, and that is true. It is not to say that people are not important. If there is a good system, people can really shine, work well, and lead to good outcomes. But a bad system will constrain even good people. So when we talk about quality, we want to make sure there are not any systematic constraints to achieving quality, right? So, in operations, we focus more on processes and systems because we recognize that no matter how many good people you hire, a process issue or a system issue cannot be solved by just throwing more bodies at the problem or trying to find a better employee and things like that. So let's do this. Let's play a game. It's called the Deming's Funnel game. And Deming would actually have managers play this game in real. This was one of the few games that he would play in very expensive quality trainings with managers. We're going to play it kind of virtually, just imagine what would happen and kind of maybe use a simulation. But this is what the game is. Okay? In Deming's original version, he had a flat sheet of paper. You can see that in the picture, right? You can see this square or rectangle, which is a piece of paper called the. On the piece of paper, there is a circle is drawn called the target. Okay, either it's drawn or there is like a plus sign. You just draw a plus sign, on the paper like this, and you want to hit. That's like a bullseye would be hitting the center of the plus sign, right? That's like a target. It's like you're practicing archery or something. You have a target to hit. Now, in those times when Deming was doing this, there used to be what was called a carbon copy paper under the white paper, and then a hard surface underneath it. So you probably don't know what carbon copy papers are. Even, when I was young, they were very, very rare already. So even, I didn't really use them. But probably your parents or grandparents would know what a carbon copy paper is. It's a paper with ink on it. So if you put force on the top paper, and then you actually have another paper here. So the carbon copy paper is sandwiched between two sheets of paper. If you write on the top sheet, it gets written on the bottom sheet. The same words get written. Why? Because the middle carbon copy paper has ink on it, and when you press down with a pencil or a pen, the area you press down on, it pushes down on the carbon copy paper, which pushes down on the bottom sheet, and it leaves a mark on the bottom sheet. So this was often how, if you went to purchase something, the shop would make an invoice. So they would have this writing pad or an invoice pad, right? And they would put a carbon copy paper between two blank sheets, and whatever they would write here, you would get a copy on the carbon copy on the bottom sheet, and then they would take one copy and give you one copy of the invoice. So it was a way to make multiple copies. You could stack up 3 or 4 sheets with carbon copy sheets in between and make 3 or 4 copies. So basically it was write once and make multiple copies in the same time using a manual process before computers, printers, and photocopy machines became extremely popular. So Deming wanted to use this setup because what he wanted to do was capture exactly where the marbles fall out of the funnel and land on the paper. So we want to capture by a dot where the marble hits the paper. So the way they would do that is they would take this sheet of paper, put a carbon copy sheet underneath it, and put a bottom sheet. When the marble hits the top sheet, it depresses it downward, and it depresses the carbon copy sheet temporarily downward to hit the bottom paper hard, and it makes an ink spot there. So if you throw marbles on this paper at the top, and then you remove the top paper and you look at the bottom sheet, the top paper, because marbles don't have ink on them, there won't be very obvious marks on the top sheet, but the bottom sheet would have dots. So if you looked it up like this, it would have like these dots. Wherever a marble landed, there'll be a dot. Okay. Now, if you've been to a range to practice shooting, you know that you have a target. When you shoot a bullet, it makes those holes. and you can see the spread of where the bullets hit the target, right? So same idea here. We want to capture the spread of where the marbles were landing. We want to capture where the marbles land. Now, in modern times, you have more options to do this, right? You can just maybe have a digital screen or something, like a touch screen, and wherever the marble lands, the software records that point. So this is where the marble hit, right? Or you could have marbles with a special material in them, so that wherever they hit, maybe they have some sort of ink on them or something like that. They leave a spot. Obviously, if they're going to roll off, they're going to leave more than spot. They're going to leave streaks, right? But if we can make this to be like something soft, so they just drop and they can just sink in, and they have some ink on them, they can leave spots on where they land. Anyway, the carbon copy method still works really well, right? So all we need is to figure out where the marbles landed. Then you have a funnel, and the funnel is a certain distance above from the paper. Maybe this is like maybe 2 feet or maybe 1.5 foot, right? And the funnel is being held by a stand. Okay, it's being held by a stand. Okay, so the stand ensures that the funnel does not move on its own. You can move it, like this arm is flexible, so you can move the funnel around if you want to, but if you don't move the funnel, it's not going to move by itself. So this is stationary until you apply a force to the funnel. The paper at the bottom is obviously stationary, and then you have a bunch of marbles, right? And the goal is to throw the marbles into the funnel so that they fall and they land on the target. Okay, so if you were to throw, let's say, like 50 marbles down the funnel, and then you were to see where they fell, if this is the target, if that circle is the target, you should be following mostly in the circle or very close to it like this. This should be the scatter pattern you want to get, right? Mostly or almost always hitting the target, right? You don't want to get something like this where this is the target and you are all over the place. Okay, that's kind of your off target, right? So you want to hit the target with the marbles. That is the simple game. And what you have to do is you have to find a strategy so that your team can win, your team can land most balls on the target. So that is the game we're going to play. Now there are 4 strategies you want to try out, right? So different teams would come up with their own strategies, right? There could be more than 4 strategies, obviously. You could come up with your own strategy. But these 4 strategies represent real scenarios or real ways of doing things in companies. So we're going to evaluate, which of these strategies works best in this marble game. Okay, so the strategies are kind of called rules. A rule is just how are you going to move your funnel to keep optimizing your drops to fall on the target. So the first strategy or rule is called lazy boy. It means do nothing. So no matter where your marbles are falling, obviously when you start with the first marble, you're going to try to position the funnel on top of the target, right? You're not going to position the funnel in a corner of the paper and start throwing marbles and then try to move it. Before you start, every team is allowed to position the funnel, and you can look through the funnel to see that it's kind of lined up on top of the spot. Now, you might ask, if this is the paper and here's my funnel on the top, if the funnel is lined up to be above the target, all marbles must fall on the target. That is not true for several reasons, and we'll talk about that. You'll always get some spread, right? It could be just, think about, well, different factors could cause that. We'll talk about that in a minute, right? But you are allowed to line up the funnel on top of the target before you start, before you even do your first marble. Okay, so lazy boy is this, that they do line up the funnel before they start the game, but once the game starts and they observe the marbles falling in different positions, they do nothing to update the position of the funnel. Okay, so there's no update to the position. Okay, the second is a tune. So it tries to adjust the funnel based on the deviation of the marble, right? So if this is the target and the marble falls to the left 2 units, so -2, and then below -2 here, so the marble landed here, right? And this was the target, right? What you do is you move your funnel in the opposite direction. The marble was below the target, so you move your funnel upwards 2 units, and the marble was to the left of the target, so you move the funnel to the right of the target 2 units. So whatever the offset of the marble from the target, you move the funnel in the opposite offset so that the next marble will hopefully land right on top of the target. The third rule of strategy is that you do a reset before you do any tuning. Okay, so if the marble lands, away from the target, you observe how far it was. So let's say the marble was, if this is the target, let's say the marble was 1 unit to the right and 1 unit to the up. This is where the marble landed. And you would often use graph paper with those lines on it so you can measure how far things are, right? How many units you are right and up. So what you'll do is you'll first try to center the funnel on the target, and after you've centered the funnel, centering the funnel is the reset part, right? So you're not going to worry about the offset of the marble from the target. You just reset the funnel. And then once you reset the funnel, then you move the funnel in the opposite offset of the marbles. The marbles to the right and up, so you go left and down. So you put the funnel at the opposite offset from the marble after you reset the funnel. So basically rule 3 is rule 2, but before you do rule 2, you just reset the funnel. And rule 4 is calibrate to the last output. So that means move the funnel to wherever the marble landed. If this is the target and the marble landed here, you move the funnel on top of the marble's landing for the next drop. These rules correspond to real life comparisons. Rule 1 corresponds to not doing anything, right? Rule 2 corresponds to adjusting machinery every time there was a deviation from target. An example of rule 2 would be if you're filling bags of some material, let's say you're filling coffee into bags or something. If the bag is 100 grams lighter, you try to adjust the machine to use 100 grams more per bag. So that's rule 2. You kind of offset it in the opposite way from the, how far you were from the target. Rule 3 corresponds to resetting a machine to factory settings and then trying to adjust for the last deviation from the target. Rule 4 corresponds to treating the last unit of output as the standard and trying to meet that standard in the next unit. If a worker can only see the last unit produced and no standard is provided, he or she might try to replicate just that standard. A new hire might be trained by an employee, then this new hire might train the next new hire might train the next new hire, right? So that would be a situation of rule 4 where we just move to whatever the last output was. Any mistakes of employee 1 become part of the training for employee 2, which is then imparted onto employee 3, which gets mistakes of employee 1 and 2 and so on, right? So rule 4 is basically you just have the last output and you try to replicate that. What I want you to do is pause the video and think and decide which strategy you think will perform the best. Best meaning the marbles will land really close to the target, tightly around the target and not be off by a lot. Okay, so is Lazy Boy going to give us the best results, or tune, or reset and tune, or calibrate to last output? Pause the video, think about it, pick your choice, and then continue. As Edward Deming liked to say, in God we trust, everyone else must bring data. We are going to now do the experiment and see which strategy works best. Okay, so we're going to use an online simulation to see what is the output for each of the 4 rules. The link to the simulation is given here. Hopefully it's still live. I hope they've not taken it down. You can actually go there and do your own experiment, pick how many balls you want to draw, pick which rule you want to use. Okay. The target is shown in red. Okay, here you can't see the target. There's a white square because so many black dots are on top of it. Here this is the target, and here this is the target. Okay. Actually, let me draw the target a little bit more accurately for the first case. So I want to circle the targets so you guys can kind of see. So this is the target right here. This is the target right here. This is the target in the bottom left corner right here. And right in the center, this is the target. You can see the standard deviation, which manages the dispersion around the target, is lowest for rule 1. Remember, rule 1 is lazy boy, do nothing. Okay, so that seems surprising. Why would do nothing be the best strategy? Rule 2, which was tune, so you adjust the funnel each time. Look, how it is spread. It has a bigger spread, and it's not even centered on top of the target. You're always to the right and mostly to the higher end, to higher of the target. You're not always going to get this distribution, but often you'll get that it's going to be below or to the left, to the above, to the right of the target. It isn't usually centered on the target. Okay, strategy 2. Strategy 4 you see is all over the place. Rule 4, which was take the last output as the target. So you reset kind of like after each output. Like not reset, you adjust to the last output. And then reset and tune, look at this. And look at the huge standard deviation. Okay. So the winner is lazy boy do nothing, and we want to understand why. Okay. To do that, the whole purpose of this entire experiment is to explain to you the two ideas of common cause variation and special or assignable cause variation. In the funnel experiment, okay, when you have the funnel and you're dropping marbles on a sheet of paper, there's some wind that might blow occasionally, okay, and this will add some variation because as the marble moves through the air, the wind can push it one way or the other. Okay, so that would be common cause variation. It's inherent variation that is present when you throw marbles through a funnel on top of paper. Right, this wind, just unless you're in outer space, there's going to be some wind factor that will add a little bit of variation to where the marble falls. Another example of common cause variation is if you zoom into the funnel. Okay, the funnel is going to be thicker than the marble. Okay, because if the marble was bigger, then it will just get stuck. It will never come out through the tunnel of the funnel. So because the marble is smaller than the tunnels, it can hit the side walls and kind of bounce back and forth. Okay, so it may come out at an angle, or it may come out at this angle. Okay, and this again, which angle it comes out of is going to add variation to where it lands. Okay, so these are called common cause variation. They are inherent in using the funnel on the surface of the earth for an experiment like this. To get rid of air, you maybe have to go to space. You can't get rid of having a funnel which is wider than the marble because the marble must come out of the funnel. Then special or assignable cause variation is caused by some external influence that can be eliminated by removing that influence. Often you cannot remove it. It's often not completely random, the special assignable cause variation, right? It has some pattern to it. So let's say that you are holding the funnel in your hand, right? And somebody's hand was very shaky. So the funnel was shaking while the marbles fell through it. It will increase variation. So that is special assignable cause variation that has to do with how we do the experiment, and we can modify our way of doing the experiment to have somebody with really calm hands hold the funnel and not kind of shake it around, right? So the main idea that the whole experiment is trying to get across is that you have to figure out whether you have common cause variation and special cause variation, or only special cause variation. The reason being, if it's only common cause variation, then fidgeting around with the funnel and stuff is not going to help you, because that is inherent variation in the system. Unless you change the whole system, you move the funnel closer, maybe make it a different funnel, things like that. So unless you do something like that, you're not going to get rid of common cause variation. Special cause variation has a cause which can be known, which can be investigated and found and removed. So special assignable cause variation is when you can find, what is causing some problem and then removing that cause. So the main lesson is, do not try to tamper or correct when only common cause variation is present. Tampering will introduce more variation. So this is what we saw. Look at rule 1 where there's no tampering. Nice, right, around the target. Look at rule 2 where you're tuning or tampering after each marble falls, and your standard deviation goes up. Okay, so rule 1 beats rule 2, which means if there's only common cause variation present, don't mess with the system. Now, what can you do if you don't have special cause variation, but the common cause variation is too much for the customer? The customer is not happy with so much variation and so much variability in the output at different times. So that means you need to redesign your process, perhaps invest in newer technology, and a new process, with better improved technology can have then lower common cause variation. So you have to go back to the drawing board, redo the whole process. Usually, no two products produced are exactly alike. They may look alike, but at a very fine scale, there will be slight differences, because processes used to produce them contain many sources of variation, even if the processes are working as intended. So the idea here is that there's some residual variation, some common variation in processes that is normal and natural, and we just have to live with that, and we shouldn't try to reset things or tune things to deal with that amount of variation. In other words, process variation can never really be zero, and given our technology and our process, we should know that there's some amount of variation in the process that we cannot get rid of. The only way to reduce that will be to go to a new process with better technology and more accurate equipment, things like that. However, sometimes there could be special cause variation as well, which is when a machine is not working properly, an employee is not trained, so external causes are messing up the process. So management should investigate causes of variation and eliminate special cause variation. Special cause variation is also called assignable cause variation, because you can find a cause for it that should not be there. So something is happening that should not be happening. So a machine either needs maintenance, or a machine is not working properly, or employees are not working properly. Sometimes common cause variation is too high, and we talked about that, and then management has to consider new technologies and processes. Process capability. Now that we understand process variation, that there's common cause variation, that is the inherent variation in the process, and there's assignable cause variation, we can talk about process capability, because process capability deals with the idea that what is the common cause process variation when there's no assignable cause, and given that variation, can the process meet user specs or not? Process capability is the ability of the process to meet design specification which come from the user requirements, because the product is designed to meet certain user needs. Sometimes these are called tolerance or specification limits, right? So these are a range of acceptable values established by engineering, design, or customer requirements. And then we also might have a nominal or target value, which is we want, whatever we're making to be this long, so this many centimeters long, but it could be a little bit longer or a little bit shorter, plus minus, let's say, 2 millimeters is fine, something like that. So a target for design specification in most cases is the center or midpoint of the tolerance limits. So in other words, whatever we are making, okay, we have a target value that we should aim to have. But sometimes our output can be above or below the target value, and that's fine because we have some tolerance and we have an upper limit, okay, upper limit and a lower limit, okay. Only when our output falls outside the two limits do we have defects. Otherwise, once we are within the tolerance limits, we do not have defects. These are all fine. Okay, so let's consider this where there's some service process and we aim to finish the service in 25 minutes. However, plus minus 5 minutes of tolerance is allowed. So if we take up to 30 minutes, we're still okay, or if we take down to 20 minutes, we are still okay. The green curve represents the frequency distribution of how long the process takes in reality. So we run the process, we do produce the service many times, and we make a histogram or a distribution, a probability distribution, and we see that the probability of, whatever this number is, maybe it's like 18, the probability of being below this number is really, really small, close to 0. The probability of being higher than this number, whatever that is, 27, 28, is very, very low. Okay, so this process is said to be capable because the process variation which causes the output to be above or below 25 minutes, the process variation is not large enough. So the process variation, okay, is within the tolerance. Here, on the other hand, on the second picture on the right, we see the process is not capable. Why? If you look at the process output, okay, a lot of times it is between 20 and 30, but then a lot of times right here, the process takes more than 30 minutes. So, we have a lot of times when the process takes more than the upper limit, which means the process is not capable of being consistently producing desirable results. A certain percentage of the time, the process is going to produce undesirable results. So it's not capable. Now we measure process capability by two metrics. The first one is called the capability ratio, okay? And the capability ratio is simply the upper specification minus the lower specification over 6 sigma. Okay, so upper spec is whatever is the target value plus the tolerance. So if the target is 25 and the tolerance is plus minus 5, which 25 plus 5 equals 30. Right, that's the upper spec. And the lower spec is target value minus the tolerance. This gives us 25 minus 5 or 20 minutes. We can then use these two upper and lower specifications to calculate the capability ratio. And we divide that by 6 times sigma, where sigma is the process variation And specifically, it's not, we don't say it, it's kind of assumed. This is the common cause process variation. We compute sigma for our process when there's no assignable cause variation present. We have, the machines are all maintained, we have trained workers, everything is good, and we measure the output of the process, we find the standard deviation of that output, that is sigma. We have to remember that specification limits capture the voice of the customer. So these specification limits are based on customer needs. Okay, what does the customer want? The second measure of process capability is called Process Capability Index, or CPK. Okay. Now, if you on an exam or homework see process capability ratio or index and you don't remember which one is which, remember that the ratio is a simple ratio. It's just something divided by something. So we have upper spec minus lower spec. It is the width of the tolerance. We have upper spec and lower spec. How wide are the tolerance limit divided by 6 sigma. And the index is more complicated. You have to take a minimum of 2 numbers. The first number is wherever the process is targeted, whatever is the average output of the process minus the lower spec over 3 sigma. And then we get another second quantity, which is the upper spec minus the average of output of the process over 3 sigma. And the minimum of these 2 numbers is going to be our CPK. So let me show you an illustration that will help you remember, or at least that's how I remember. Okay, CP and CPK. Imagine you have a garage, and you want to park your car in this garage. The width of the garage is your upper spec minus lower spec. And the width of your car is going to be 6 sigma. Now, if 6 sigma, the width of the car, is less than the width of the garage, you should be able to park the car in the garage, right? However, if the width of the car was more than the width of the garage, you will not be able to park our car. So all CP is telling you, can you park the car or not? Is the width of the tolerances wide enough that your process can fit in between them? Okay, so in CP, 6 sigma is like the width of the car, and upper spec minus lower spec is the width of the garage. If the car is smaller, you get a ratio above 1, which means that you can park the car in the garage, process is capable. However, what can sometimes happen is this. You have a pretty wide garage. Okay, so your garage is wide. Okay. And it's wider than your process, so your car is not very wide. However, your car is lined up very poorly and is backing up this way and is about to hit the wall, right? It's about to do a crash right here. Even though the width of the garage is more than the width of the car, and CP is saying everything is fine, we are good, the car could still crash on the wall. Why? Because the center of the car, which is given by x bar bar, the average of x, which is the output of the process, is not centered, right? You are not centered. Okay, so CP doesn't tell us that the car is not centered. Okay, and so it should have been centered, but it's not. And so we can still have problems even though CP is fine. CPK corrects this problem. What it does is, instead of just comparing the width of the garage to the width of the car, comparing this width to this width, it finds how far is the center of the car from this wall and how far is from the other wall, and uses the smaller distance to calculate your process capability, because the car only has to drift the smaller distance to hit the wall. Okay, so x bar bar minus lower spec is the distance between the middle of the car, which is the average value of the process, and the lower standard deviation, the lower spec, divided by 3 sigma. And similarly, on the other side, you get upper spec minus x bar bar. This is how far the mean is from the upper spec, and you'll divide by 3 sigma. And of both numbers, you'll take the minimum. So what are the values of CP and CPK that are acceptable? A value of 1 means the process is barely capable. So most of the time, companies want to be a little bit above 1. So they may do like 1.33, which is considered a 4 sigma level, right? And in the textbook we're using, if the question is the process capable or not, you will always compare CP/CPK with 1.33. If it's 1.33 or more, then the process is capable at the 4 sigma level. Okay. Obviously, 6 sigma capability requires a level of 2. So CP and CPK have to be 2.0 or higher for us to be at the 6 sigma quality level. 4 sigma quality level is 1.33. 3 sigma quality level is 1. So 1 is not that good, because it implies, it implies quite a chunk of errors can happen per million opportunities. So CP/CPK of 2 is really good. 1.33 is okay. Technically, 1 is also okay. Anything below 1 is not okay. You want to be 1.33 or above. Let's do an example. The intensive care unit in a lab process has an average turnaround time of 26.2 minutes and a standard deviation of 1.35 minutes. So these are process characteristics. So x bar bar, the average of the process, is 26.2, and sigma, the standard deviation of the process, is 1.35. So this is the process. This is sometimes called voice of the process, the statistics of the process. Then we can look at the customer specs, okay, or customer driven specs, which are the target value is 25, and then you have plus minus 5 minutes. So plus 5, you get 30 minutes, and 25 minus 5, you get 20 minutes. Okay, so is the process capable at the 4 sigma level? So first we can do CP. So we know that, my upper spec is 30 minutes, minus lower spec is 20 minutes, and over I have to do 6 times sigma, which is 1.35. Okay, so you'll get 10 on the top, right, over 6 times 1.35, the standard deviation. Okay, so that would give us CP. Okay, so we got the upper spec, lower spec, average service time, and sigma. Okay, so if we have to calculate CPK, so are we doing CP as well? Yes, here we are doing CP. So upper spec minus lower spec, right? 30 minus 20 over 6 times the standard deviation gives us a CP of 1.23. Now, because the question asks us to work at the 4 sigma level, we need to get at least 1.34 or 1.35, whatever the standard deviation of the process is 1.35. It's going to be 1.3. 5, right, which is right here. So CP is 30 minus 20 over 6 times 1.65, which is standard deviation, which is 1.23. Now 1.23 is less than 1.33, which is, 4 sigma level. So, we need to improve here in this intensive care unit lab. If we calculate CPK is the minimum of two numbers. The first number is the output of the process X bar bar, which is 26.2, minus the lower spec over 3 sigma. And the second number is upper specification, which is 30, minus the X bar bar value from the question, which is 26.2 divided by 3 sigma. We get the smaller number is 0.93, and that will be the value of CPK. So you'll see that 0.94 is the smaller of the two numbers. So CPK, we pick the minimum, that's 0.94. And again, this CPK is less than 1.33. The process does not meet the 4 sigma level. Now remember that CP or CPK is bad. That means process is not capable. Okay, so both on CP and CPK, the process did not meet the desired quality level of 4 sigma. Okay, so what I want you to consider now is what happens. In this case, it was simple, right? So in this case, CP was 1.23 and CPK was 0.94. And both of them were less than by the cutoff of 1.33, which is the 4 sigma capability level. So because both of them were kind of below, we could conclude the process is not capable. Okay, what happens if one of the CPK is lower and one of them is higher? Okay. Now, as you saw here, CP was more than CPK. That's going to be true most of the time. CPK can at most be equal to CP, but can never exceed CP. So first of all, let's say, when does CPK equal CP? Okay, that happens when the process is perfectly centered. Process is perfectly centered. Okay, so what do I mean by that? If you look at this situation here, our target value is 25. So our target value is 25, and then we have a tolerance of plus minus 5. So we go plus 5 to 30, minus 5 to 20, right? But our process output is an average of 26. That shows our process is not centered because our process is somewhere here at 26.2. It's closer to 30 than it is to 20. It's not centered. Okay, that is why our CP is bigger than CPK. Whenever the process is not centered, you will have this. CP is bigger than CPK. If we moved the process this way until the process became centered on the target value of 25, so the process was centered, in that situation, CP would equal CPK. And why, it's very easy to understand. CP does not care about centering. So in both cases, the CP would not change. The CP would be the same. This CP here, when the process is not centered, would be the same CP when the process is centered, because CP does not care about centering. But CPK improves the more you center the process. So when the process is not centered, the CPK would be a smaller value. And as you center the process, the CPK would rise until it equals CP when it was completely centered. So if you see a CP value above CPK, you know that the process is not centered, right? And if you see them both to be equal, you know that the process is centered. Now, this can actually lead us to a very useful rule. So let me summarize it here before we move to the next topic. Okay, and you need to know this. So number one, if CP equals CPK, that means process is centered. Okay, Number 2, CPK is always less than equal to CP. CPK can never exceed CP. Okay, why? That's by definition, because CPK penalizes you for centering. So if you're perfectly centered and there's no penalty, it will equal CP, but it can never exceed CP. Number 3, okay, if CP is okay, which means it's bigger than 4 sigma, or it's bigger than 6 sigma, whatever the level is. So if the question says process should be 4 sigma capable, you compare CP with 1.33. If the question says process should be 6 sigma capable, you compare CP with 2.0. And if the question says the process should just be 3 sigma capable, then you compare CP with 1.0. So whatever your threshold is, right, this is called a threshold. Whatever your threshold is for your process, based on what you want out of the process, what level of quality you want. If it's a 4 sigma process, 1.33, 6 sigma, 2.0, 3 sigma, 1.0. CP has to exceed one of these thresholds depending on whatever sigma level you're at. So if CP is okay, meaning it exceeds the threshold, okay, but CPK is not okay. Not okay. What does that mean? CP is telling you that the sigma, the process variation, is fine, and CPK is not okay, so the problem must be centering. Problem is centering. So this is an easy thing to resolve. You can just recenter the process. Usually recentering is not difficult. You just have to adjust the machines or the ingredients that go in, things like that. If you're filling weight and the weight is too high, you adjust the filling machine, things like that, to recenter the process. So sigma, if CP is okay, that means sigma is fine, and CPK is not okay, that means the process is not centered, so the problem is the centering and you center the process. However, what if CP is not okay? And because CPK is less than equal to CP, CPK is also not going to be okay, right? So both of them are not okay. Then that means the process variation is too high, okay? Because whenever the process variation is fine, CP becomes okay. So if CP is not okay, the process variation is too high. The process may also be away from the center. So process additionally, right? Additionally, may not be centered. May not be centered. And how would we know that? Whether CPK is less than CP or not. So let's say we're comparing to the 4 sigma level. So our threshold is 1.33. Okay. Our CP in this case came out to 1.23 and CPK came out to 0.94. Our CP was not okay, so the process variation is too much. 1.35 is too high a process variation. You have to reduce this variation. Once we reduce the process variation down, CP would eventually rise to meet the threshold of 1.33. But we are still not done because CPK was less than CP, so the process was not centered. So in addition to reducing variation, we also need to center the process so that the CPK becomes equal to CP. Okay. If the CPK here was also 1.23, the exact same value as CPK and CP at the same value, then the only problem was variation reduction, because we want to be 1.33, so we reduce the variation of the process. Centering is not a problem in that case. So by comparing CP and CPK values, you can figure out whether centering is a problem or not, whether process variation is too high or not. And then you can address those in your process improvement efforts. Now we get to statistical process control. To do that, we do that once process is capable. Okay, once the process is capable, CP and CPK are bigger than equal to the threshold, whatever our threshold is. All right, it can be 1.3344 sigma, it can be 2.0046 sigma, and so forth. Whatever our threshold is, if CP, CPK are bigger than equal to the threshold, both of them are bigger than equal to the threshold, that means process is capable. Now the question becomes, you have a capable process which is going to produce good output. How do we keep the process in control? What does it mean to be in control? In control means there are no special cause variations. Okay, there's nothing messing the process up. Okay, so statistical process control is a monitoring tool. It's a monitoring tool. Okay, it monitors the process and kind of raises an alarm, ding, 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 when it detects special cause variation. You know, in one line to define statistical process control, you can say it like this. Statistical process control is a methodology to monitor a process in order to detect any special cause variation. Statistical process control will raise a red flag and say, hey, I detect, special cause variation when that happens. Okay. So formally, SPC is the application of statistical techniques to determine whether a process is delivering what the customer wants. This is kind of like really broad. Okay, it basically only checks whether the process is, doing as it was doing in the past when we tested it to have no special cause variation when we initialized it. If it does not test process capability, so I don't like this definition from the textbook too much, because it's not determining if it's delivering what the customer wants. You could have an in control process which is not capable, in which case the process is not changing, it's fine, but it's not delivering what the customer wants. Okay, so it's kind of like a little bit of not a good job by the textbook author here. Basically what I told you is better. It's a monitoring tool which detects presence of special cause variation, raise a red flag when there is special cause variation, so you can fix it, because special cause variation can produce defects. It can take, even if a capable process will produce defective output if there's special cause variation present. Okay, because special cause variation is going to move the process away from the target value. Or increase the variability, so it goes outside the specs. SPC uses control charts to determine if the process has changed in terms of some of important metrics, like the centering of the process is okay or not, or the variation. In SPC, we periodically sample the process and use statistics on each sample, okay, to see if the process is doing okay or not. So we're going to be concerned with some sample statistics that you should know. The first thing is, if we have a sample is just some values we measured from the process. Imagine you have a machine which fills up bags of coffee, and you take a sample of 10 bags and you measure their weights in gram. So maybe the first bag was 505 grams. The next bag was 492 grams. The next bag was 500.3 grams, and so on. So you take a sample of 10 values, you have 10 numbers like that. So you can calculate the sample mean, which is simply the average, by adding those numbers up. This sigma just means add stuff up. You add up all the 10 numbers, divide by n, which means how many numbers you had. N is 10 in this case, right? And so you get the average. Average is represented by a bar on the top, so we read it as x bar. X bar means average, some sort of an average. In Excel, if you have those numbers, you can easily use the equals average function to compute the average. The second and third statistics we need is the range and the standard deviation. These are measures of variability. So standard deviation has this complicated formula, which I don't expect you to use. The best way is to put the numbers in Excel and use this formula in Excel, equals stdev.s. Okay, so let's see if I can show you what this formula is going to look like. Okay, so let's say we have some data, right? So we have some data. We have, let's say, 5 observations, from our coffee bag filling machine. So you got 505 grams, 492 grams, 498 grams, 501 grams, 506 grams. So this is our sample. okay, with 5 values. So what is my n? My n is 5 because that's my sample size. So your sample mean is simply equals average, and you select the numbers, and that's going to be your sample mean. Okay, and then your standard deviation of the sample is stdev.s. Okay, stdev.s, and you select the numbers, and that is your standard deviation. That represents how much variability you have in the value. So on average, our values are plus minus 5 around the mean of 500 on average, right? And then you can find the range. Range is the maximum value minus the minimum value. So if they equal max and you select these numbers, that's the maximum value, right, minus the minimum value, that is the range, okay, which is 14. You can also do it manually. You can, so the maximum value is this one, 506, and the minimum value is 492, right? So this minus this is going to give you 14, which is the range. So these 3 sample statistics you should know how to compute for a set of data. You can do it in Excel easily using equals average function, equals stdev.s function, and equals max minus the min for the range. Okay. If you don't want to use Excel, you can also do it manually, but it's a whole lot of work, and the formulas are given on the slide. So control chart, once we know how to compute sample statistics, we're going to make a control chart. So a control chart is a time-ordered plot of sample statistics obtained from an ongoing process. So let's say we have this bag filling machine which fills coffee bags. Every hour we go and we sample 5 bags or 10 bags. We find the sample average, the sample standard deviation, the sample range, and we plot these values on a graph. So you may have a graph like this. Okay, 8 a.m., the process average was here. 9 a.m., the sample average fell a little bit. 10 a.m., the sample average went up a little bit, but it's all fine because we're within, this is still, acceptable variation. Then 11 a.m., we got another value, 12 a.m., we got another value, and so on. Okay. So each time you take a sample, you find the sample mean, the sample standard deviation, and you can plot them on a chart, and that's control charts. Okay. Now, control charts also need control limits, which are like a band around your values. And the band represents that if you are within this band, then you only have common cause variation, and there's no evidence that you really have special cause variation. But if you do have observations going outside that control limits or the control limit band, like an upper and a lower control limit, then there's evidence that you likely have special cause variation present, and you better investigate and nip the problem in the bud. This is an example of a control chart. On the x-axis we have sample numbers. So maybe every hour we take a sample, or every 20 minutes, whatever our frequency is. Each sample gives us an average value, or we might be plotting range over time. You can plot range. Each sample you can compute the range, right? And you can see that we are within the control limits, the upper control limit and the lower control limit for the most part. But right here at time period 12, we exceeded the upper control limit. So the evidence is saying because you're outside the control limit, some special cause variation has happened. Okay, special cause variation. Maybe our machine stopped functioning properly, or the operator is not working properly, or maybe you got an untrained employee handling it, and so things are kind of going haywire. Okay, so that's how control charts work. Now, we are going to learn how to make these control charts, right? So it's a relatively easy process. You establish the control limits, right? And then you measure a sample and measure the units in the sample. Take a sample, measure the units, compare the sample results against the control limits. If the sample results are within the limits, you're in control, otherwise you're out of control. If you're out of control, take corrective action, investigate the cause of the deviation and take corrective action, and then you go back to step 2 and you keep controlling and monitoring the process again. Okay. Now you can go out of control by doing one of 2 things. One is called a shift of the mean, which is the process drifts off target. So in control process was rightly centered, so this would be like your target value type of situation. So somewhere here is where you want to be. And when you were in control, you were centered around the target value. But now as you get out of control, your average drifts. Maybe your average was 30, right, and now it's 32. Okay, that's called shift of the mean. The process has not become wider. If you look at this, it's the same width as the other one, right? And so there's not been any increase in variation, but there's been a drift from the target value. The second thing that could happen could be an increase in variation, which is measured by standard deviation or range. So the process is centered at the same target value as before, but the process is now having a lot more variability, and so the variation has increased, but not the target value. Or in other words, the process is still centered correctly on the target value, but the variation has increased. Okay. So we have, three types of control charts that we're going to study here. Okay. If what you're measuring, the output of the process you're measuring, okay, is a real number, okay. What is a real number? Meaning that it can take fractions, it can accept fractions, it can accept values above 0, above 1. So, if you're measuring weight, you may get like 200.75 grams, or you may get 212.3 grams, right? So there is a fractional part, and, it's a real number that is measuring some phenomena like height, weight, density, amount of sugar in a drink, things like that. Okay, resistance of a circuit, things like that, right? So this is a real number which can have a decimal part, and it can take different values. It can take 201, it can be 199, it can take many different values. When you are measuring a real number, which is also called a variable performance measure, meaning it's not just yes, no, then you have to use what are called two charts together, a mean chart or X bar chart and a range chart or R chart. The mean chart, X bar chart, detects a shift in the mean, and the other one detects a change in variation. So this sort of situation where you were in control on the blue, and then you kind of, this thing happened, this would show up on an R chart very nicely. As you go from the blue to the magenta line, you'll see the R chart showing you that your variation is going out of control. Okay, and this, where the variation is the same, but your mean is changing, right? Okay, so this would be detected on the X bar chart. That would show you that the average is drifting away of the process. Okay. Now, if you have attribute performance measures, you cannot use X bar and R chart. You have to use what's called a P chart. Attribute performance measures are yes, no, defective, not defective, good, bad, right? So it's like a yes, no, 1, 0 type of question. So you check, you turn on the TV, does the TV work? Yes, does it not work? No. It's just two possibilities, yes or no, for each item that you examine. So then you would use what's called a P chart to track the proportion of defectives, and you want to make sure your defect rate stays stable as it does not blow up. Then you may have to use a count chart or a C chart, which happens when each unit that you produce can have more than one defect. So this is an important distinction. So I need you to pay attention and really understand this. So let's say you are producing, what are we producing? Let's say you're producing keyboards. If you have a desktop computer, you can buy a keyboard and attach a keyboard to a desktop computer. Okay, so let's say when we produce keyboards, okay, we want to test the chip, the electronics chip on the keyboard. If the chip is bad, the keyboard will not work. It will not come to life. If the chip is good, we connect the keyboard to a computer and we press any keys and the keyboard would work. Okay, so each keyboard we check is connected to each keyboard we produce. We connect it to a computer, and we see if we've pressed the keys, the same numbers appear on the screen or not. If they do, then the chip is good. If they don't appear, nothing happens, then the chip is bad. So it's yes or no. 1 if the chip is good, 0 if it's bad. So we'll use a P chart. Let's imagine, let's use furniture. Okay, when we do quality check of furniture, we have to make sure it doesn't have scratches and defects. Now, a piece of furniture can have 0 defects or scratches, 1 defect, 2 defects, 3, and so on. So it could be any positive integer. In this case, we'll use a C chart or a count chart because we're literally counting the amount of defects. You know, 1 defect or 2 defects is not on 2 different pieces of furniture. Each piece of furniture we examine, let's say we examine sofas, okay? Each sofa we examine can have 0 defects, 1 defects, 2 or 3 or 4 or 5. And onwards, right? So that's called a count data because it's not just 0 and 1, right? We don't say, okay, this sofa has a slight scratch, so we just throw it out. Right? It's not 0, 1. It's not good, bad. You know, you could have 0 defects or 1 or 2 or 3 or 4 defects, things like that. That's count data. So then we use a C chart to make sure the defect rate is not going out of bounds, right? So, you know, then we can use a C chart to make sure that the number of defects is not increasing. We may have some defects, but that number is not increasing. The process is not blowing up. Okay. So one of the most important things about statistical process control charts is to figure out which chart to use. So when you get a question, first of all, you have to figure out, am I going to use an X bar R chart or a P chart or a C chart? Okay. And if the data is a continuous variable, it's a variable like height, weight, is, you know, numbers with fractions, it's going to be the X bar R chart. If it's 1, 0 data, everything you examine is 1 or 0, is P chart, otherwise it's C chart. So let's see how to make these charts. Here are the formulas for the X bar chart, okay, and the R chart. X bar chart has an upper control limit, which is given by the centered value of the process, the average of the process, plus a constant A2 times the average range. So if you take multiple samples, you have a range for each sample. The average range is what's R bar. X bar bar is the average of the averages of each sample. So that's why it's X bar bar. Each sample, right? So sample 1 will give you X bar 1, R1. Sample 2 will give you X2, R2, and so on for sample 3. So if you average out all of the R from multiple samples, you would get R bar here. And each sample gives you a sample mean. If you average the means, you get X bar bar. You take an average of the averages, you get X bar bar. And A2 you can look up based on the sample size, and so you can calculate the upper control limit, and the lower control limit is the same formula, except you subtract, so you take X bar bar minus a constant times R bar. For the R chart, the control limits are given by a constant D4 or D3 times the average range R bar. These constants you can look up in a table based on the sample size of the sample that you're using to compute the X bar and the R values. Okay. So here is the table which gives you the values of the constants A2, D3, and D4. So whatever your sample size is, you know, maybe you're taking samples of size 2, or each sample has 3, or each sample has 4, or, you know, 5, 6, 7, 8, and so forth. Whatever your sample size is, you go to that row and you pick the values for A2, which is here, to use here. Right, and you can find D3 is 0 and D4 is 2.115. So you can find the values given your sample size from this table. This is what I talked about earlier. You know, what happens if the mean shifts? So look at this process at time T1. Okay, it's pretty narrow. At time T2, the width is not increasing, but the central tendency is starting to drift upwards. Again, central tendency drifting upwards, central tendency of the process drifting upwards. Okay. So how would this appear on the control charts, right? So we want to see if this happens in real life. However, look at the R chart first. Nothing happens here. We're within the control limits. These are the control limits, the line at the bottom and the top. So, no problemo on the R chart. Okay, everything's fine. Because the R chart is trying to just check the width of the distribution. As long as it's not getting wider, our chart will stay the same. The drift in the mean, however, is going to show up in the X bar chart as the average value drifts away. We see the red blocks getting higher and higher and eventually crossing the upper control limit. Now, what happens if the other reverse happens? We have increase in variability, okay, but the process is still centered at the same value, but the variability increases, the distribution gets fatter and flatter. Okay, X bar chart will be totally fine, okay, because X bar chart detects shifts in the mean. So X bar is totally fine. The R chart, however, tracks the variability in the process, and as the variability is going up, the R bar chart shows that you go out of control at this time. Okay, so X bar chart does not reveal an increase, R chart reveals the increase. Let's do an example of an X bar R chart. So we are the management of West Ellis Industries. We're producing a special metal screw, okay, and diameter of the screw is critical. Okay, so we have data from 5 samples. For each sample, we give the sample number. We give the first value, second value, third value, fourth value. Okay, and then we are giving the range and the average, although we didn't have to. You can always compute the range from the sample values as well as the average. Okay, so how do we get R bar? How do we get X bar bar? Well, first you should realize where the last 2 columns are coming from. Okay, so this average right here, this number is the average of these 4 numbers. 0.5027, this number right here, is the average of these 4 numbers. So we'll usually call this one X bar 1, the average of the first sample, X bar 2, average of the second sample, X bar 3, average of the third sample, and so on. So, we have X bar 4, and then we have X bar 5. Then for each sample, we calculate the range, which is the max minus the min. So if you look through here, 0.5027 is the max, and 0.5009 is the min, so 0.0018 is the range. So this is R1, this is R2, and so on. Now, if I take an average of these 5 X bar values, I'll get X bar bar. And the average of these range values will be R bar, which is exactly what I've done here. So 0.021 is the average of the range values, so it's R bar. And 0.5027 is the average of these averages, so it is X bar bar. So we can calculate our control limits. X bar bar we computed here, 0.5027. And then our range we know, 0.0021, and then we can look up A2 in the table, because the question is, what is the sample size? Is my sample size 5 because I have 5 rows, or is my sample size 4? Okay, the answer is the sample size n equals 4. Sample size is the number of observations in a sample. You cannot count things not in the sample, and it's not the number of samples, so it's not each row gives you a new sample. So 5 is the number of samples, but each sample is 4 observations, n equals 4. So if we go back to this table, when n equals 4, okay, so you can see the 0.729 comes from that. And then our results are this. This will be a lower control limit, 0.5012, and a higher control limit, 0.5042. Okay. For the R chart, we get D3, D4 again from the table, looking up sample size of 5. We multiply them. So D4 and D3 we can look up from the table for sample size of 4. So we have a sample size of 4 right here, right? Each sample has 4 observations, and so we can look up that D3 is going to be 0, D4 2.282. Okay, and so we see that D3 comes out to 0, D4 comes out to 0.00479, right? So these then are the control limits for the R chart, and these above are control limits for the X bar chart. So we can plot the R chart, okay, and plot some observations, and we see that the process is in control because it's not touching the control limits, and there's also no systematic variation present, or it doesn't appear to be present. Okay. Now, this is an example where the process is not in control. So in our question, that's the end of, this is the R chart actually. So the process is in control on the R chart, but the process is not in control on the X bar chart. So what do we do, right? If you have two charts like the X bar chart and the R chart, so here we do have an out of control issue because the X bar chart is showing an observation outside the control limit. Now, when we have attribute data, which is 1, 0 data, defective, not defective, good, bad, right? We can make a P chart. So each unit that we examine of output of a product or service, we have only 2 categories. It's either good or bad, pass or fail, things like that. And so to calculate the control limits of a P chart, we first need to find the percentage defective, which is called P bar. And we take the total number of defectives and we divide by that by the total number of pieces we examine. Now recall that we take samples. Each sample has a sample size n, right? So if you take 5 samples and each sample has a sample size of 10, 5 times 10, you have examined 50 things. So that's all you're doing here. Number of samples times the sample size is how many units you have examined. That's the denominator at the bottom. At the top, you have total number of defectives. That kind of gives you like a defect rate. P bar is like a defect rate or percentage defective. Now, based on P bar, you can find the standard deviation of P bar using this formula. And this formula only works in the case of attribute data or 1, 0 data. Okay, and that is you take the P bar, you multiply it by 1 minus P bar, you divide by the sample size n, and then you take the square root. Okay, now this can sometimes be confusing to people. What is this n? That is how many units are in one sample. So like I told you, I give you an example here. If you had 5 samples and each sample had 10 units in it, then n is 10. So here you'll plug in 10, not 5, okay, and not 50. So this is a common area of mistake for students. They plug in some number in n, whatever number they think is n. You have to ask yourself how many units are there in one sample, not the number of samples, not the total number of units you examined, but one sample, how many units there are. And then you take a square root. So you plug and chug and you get sigma P bar, you get P bar, and then you can calculate UCL and NCL. The only thing missing is the Z-score. So what is the Z-score? Z-score has to do with whether Z is usually going to be 3, because usually we make 3 sigma control charts, okay? And I'll talk about that in more detail shortly. What is the 3 sigma or 2 sigma control chart? That has to do with the idea that how sure do you want to be before you declare you're out of control. So 3 sigma means that if they, under normal conditions, right, about 97.5, actually, no, sorry. So under normal conditions, if you have a 3 sigma control chart, okay, we can just use Excel to calculate what percentage will be outside that, okay. So we can do norm.dist norm.s.dist3 and true. If you don't know this formula, that's fine. Okay, and then we can do 1 minus that, and then we can do twice that. So basically, you know, about 99.7% of the time, okay, you are going to be 99.7% of the time, you're going to be within plus minus 3 sigma. Okay, so with a 3 sigma control chart, there's a very small probability, only a 0.3% chance, or a probability of 0.003, that you'll have a false positive. A false positive is you get an out of control observation while the process is not out of control. So you investigate and you say there's no special cause variation. That's called a false positive, right? So the control chart says something is going on. You go investigate and nothing is going on. So with 3 sigma control charts, you only get these false positive at 0.3% of the time, which is relatively rare. So that's why we like 3 sigma control charts. However, you know, given on the situation, you might go for 2 sigma or 4 sigma control charts, and all the 2 sigma, 4 sigma, or 3 sigma is doing is changing the probability of a false positive, because you want to control that, right? So Z is usually 3. The question will specify Z. The question will tell you what Z is. It'll either say use Z equals 3, or it'll say use a 3 sigma control chart or a 4 sigma control chart. 4 sigma means Z is 4, 5 sigma means Z is 5, and so forth. So you take P bar plus Z times sigma P bar, which you found here. Okay, so relatively straightforward formula. Let's do an example. So we have a bank, and the bank is concerned about the number of wrong customer account numbers recorded. So maybe somebody fills out some form, and sometimes they make a mistake and record the wrong account number, which creates all sorts of hassle for the bank. So each week a random sample of 2,500 deposits is taken, and the number of incorrect account numbers is recorded. So in the first sample, and there were 2,500 deposits in that, there were 15 mistakes, or 15 incorrect account numbers. 15 deposits had incorrect numbers. And the second sample, 12, and so forth. So what is the 3 sigma control chart? So first you'll have to find P bar. P bar is total defectives, which is 147. Okay, divided by total things we examined. So how many did we examine? We have 12 samples. So number of samples is 12, and each sample has 2,500 deposits which are examined, right? So we multiply by 2,500. So that will be our P bar, and our N is 2,500, which is what we'll put in the sigma P formula. Okay. So you can see that our P bar is 0.0049, right? And then our sigma P is, you know, P bar times 1 minus P bar over N, where N is 2,500, and, you know, the square root, and we get 0.0014. So now we can make a 3 sigma control chart. Z equals 3, sigma P bar comes here, and P bar comes here, and we get 0.0091, 0.0007 as our upper and lower control limits. Okay, I recommend you try to solve this on your own using the formulas here to solve this question and compare your answer. If you make a mistake, see what's going on. Then we can plot our data. So we have 12 samples, data for 12 samples. So how do we plot the data? For each sample, you divide the number of defectives, right here. So for sample one, you have 15 defectives, right? So you take 15 over the sample size of 2,500, and you get some number, 0.00 whatever. So that's the number you plot here for sample 1. Then sample 2 had 12 defectives, so you do 12 over 2,500, you get a lower number like that. So you plot all the data, and you see that sample 7 is outside the control limit. So on that day, you know, people made more mistakes than usual. So maybe you want to check who was doing the deposits that day. Maybe they're not well trained, things like that. Now let's talk about control charts. Control charts have to do with count data, right? And count data means when each unit you examine can have 0, 1, 2, 3, or as many number of defects as possible. Okay, the number of occurrences per sample can be counted. Each unit that is examined can have more than one occurrence. So it's not 0 and 1 per unit. Each unit could give you more than one defects. So how do we get the upper and lower control limits? We first have to find C bar, the defects per sample. We take total number of defects and you divide by number of samples. Note we are not multiplying it by n, the sample size. We're not concerned about what was the sample size. We're just dividing it by number of samples. Okay, that gives us C bar. The standard deviation of C bar is just square root of C bar, so that's really easy. And then Z is just like the P chart. Z is usually going to be 3, because usually we use 3 sigma control charts. Otherwise, the question will tell you use a 4 sigma control chart, Z is 4. Use a 5 sigma control chart, Z is 5. Use a 2 sigma control chart, Z is 2. So the question will tell you what the Z is. Let's look at an example, because it's really, things will make sense once we see an example. Okay, so there's a paper company that produces rolls of paper, I believe. So you get 20 defects per roll on average when the process is in control. So that's your C bar. C bar is 20 defects per roll. Okay, defects per roll. Okay. Okay, so set up a control chart. So we have to set up a control chart, right? That's part A. So average number of defects per roll is 20. So that's your C bar. Then you do plus Z equals plus Z times square root of C bar, because sigma C bar is just square root of C bar. Okay, and we get this, right? 20 plus, we're doing a 2. So here, look, notice here. The question tells us use 2 sigma control limits. That means Z will be 2. So that is why we use Z equals 2. Okay, so these are our control limits. Then we have data on 5 rows, and you want to plot them and see if you're in control or not. So we plot the data. Okay, our upper control limit comes from here, lower control limit comes from here, and 1, 2, 3, 4, 5, 6 rows of data we had in this question of part B, right? 16, 21, 17, 22, and 24. That's 5 rows, and the 6th row, we use a different supplier, had only 5 defects. So supplier 1 gave us the first 5 rows. So these 5 rows were from supplier 1, and they are in control. But notice when we switch to supplier 2, we're out of control. Okay, so is this good or bad? Well, actually, fewer defects is actually good. So we're out of control, but in a good way. So it kind of sounds weird, right? You're out of control, okay, but in a good way, because fewer defects is good. So what does that mean? That means we need to investigate if supplier 2 is more reliable in general, and then we can switch to supplier 2 for all of our roles, and we'll have fewer defects. And when you switch to supplier 2, kind of like for good, you will recompute your control limits, and then you'll get new control limits for supplier 2. Right? Because supplier 2 has a different process, and that process needs its own control limits. So sometimes when you're out of control on the lower end, sometimes that's a good thing, because you have fewer defects, and then you want to check and see, is that true reliably, or is it just a one-off thing? And if it's true reliably, then you want to switch to whatever happened in that situation. So here, this was a new supplier that gave us very low defect rates. We want to switch to the new supplier if that supplier can reliably give us, these low level defects per row. So process technically out of control due to sample 6. However, sample 6 shows that the new supplier is a good one. So maybe we want to switch to that one. Now, a question arises when we have, real numbers or variable data on performance, like, height, weight, it's like a real number, 20, 20.5, something like that, data like that. We use 2 charts, X bar chart and R chart. But when we have attribute data, yes, no data, we just use 1 chart, P chart. And when we have defect count data, we also use just 1 chart called C chart. So why are we using 2 charts here and just 1 chart here, 1 chart here? Remember, why did we use these two charts? X bar tells us about the mean of the process moving away, and range R chart tells us about the variation in the process going to increasing or decreasing. So we needed two charts, one to track the mean, one to track the variation. Where are the two charts for attribute data? Does the P chart track the variation or the mean? Does the C chart track the mean or the variation? How can we do one chart, right? So the answer to the question comes from probability theory. Okay, for variable data where you have real numbers, X bar has a normal distribution. Okay, for attribute data, the 0, 1 has a binomial distribution. It's Bernoulli, but if you take a sample, that has a binomial distribution, how many defects in the whole sample. And for count data, we have a Poisson distribution. Okay, now if you don't understand this, if you don't know probability that well, you don't understand this, you should, because you have taken stats, so you should know these distributions and you should understand this. But if you don't, I'm not going to test you on this particular slide. However, you should reflect on why you don't understand binomial Poisson normal distributions when you took a whole university level course on that, right? So normal distribution, that's X bar, that's from the central limit theorem. And you should know why X bar is normal. When you have yes, no data, 1, 0, and you take a sample and you count how many were defective, that's binomial distribution, and count data is Poisson distribution. So binomial and Poisson distribution, these are called one parameter distributions, one parameter, which means the mean and the variance are related. If you increase the mean, you end up changing the variance. And if you change the variance, you end up changing the mean. Okay. And so you only need one chart to track them, because if you go out of control on a P chart or a C chart, you're out of control both on a mean and variance basis. Okay, because both of them move together. Mean and variance are related, they move together, they cannot move independently. Whereas a normal distribution is what we call a two-parameter distribution. It has two parameters, mean and variance, and they can move independently. They're not related in that sense, like they are for binomial and Poisson. So you can have just the mean go out of control while the variance is fine, or you can have just the variance go out of control while the mean is fine, or you can have both go out of control in the normal distribution. So all three possibilities are open, and you need two control charts, one for the mean, one for the variance. Here for P charts and C charts, you only need one chart because the mean and variance are related. You cannot just change the mean without changing the variance. They kind of move in sync. So you only need one chart. Okay. Last thing, when we talk about in control and not in control, right? So till now, we have had these control limits, LCL lower control limit, UCL upper control limit. And as long as our data was within the control limits, we said, fine, dandy, I am happy, you're in control, right? However, there can still be a problem. If you have the control limits, LCL and UCL, if your data shows a pattern, let's say it goes down towards the lower limit and just lives there, sample after sample, you're getting data very close to the lower control limit. This is highly suspect behavior, because this should be moving randomly up and down if it's common cause variation, right? Common cause variation is like random variation. So it should be moving up and down randomly between the control limits. It should not be just hugging the lower control limit, right? What's up? You should ask the question, what's up, right? If common cause variation is present, we expect points on the control charts to be distributed above and below the central line, which is like this, the central line between the two control limits, in equal proportions. If you get a run of five observations in a row below the central line, or 5 observations in a row above the central line, something fishy is going on, which you need to investigate. So you could be out of control by showing these patterns of behavior, even though you're within the control limits. So you're within the control limits, but you have these patterns that can show that you're out of control. So how do we detect those patterns? Well, there are various ways. I'm going to show you two ways to detect these patterns. One is called median runs, or above below median runs, and one is called up down runs. Okay, and that can detect patterns. So what is median runs? You start at some point, okay, and you take the first observation and you circle all the observations that stay below the center line, and you stop when the next observation goes above. So we are below the center line, so I circle that. I cannot circle the next observation because that goes above the center line. You can never have a circle like this, where you have one observation below, one up. No, can't do that. Okay, you only have to circle all the ones below, which are in order, which are like one after the other. So then I have to start a new circle, a new run, and I circle all the observations above the line until it jumps down below. So I'm able to circle 2 of them. Then I just circle 1 because then again there's a jump. Then I circle 1, then again there's a jump. Then I circle 3, then again there's a jump. I circle 2, then there's a jump down. I circle 1. So you can write it at the bottom like this: below, that's B, then above, A, then below B, then A, then B, then A, then B. So you'll circle all the B's till you hit an A. Then you circle all the A's till you hit a B, circle a B till it changes to A. Now you can circle an A. You never circle A, B, or BA. You cannot put like BA into one circle. Then you circle all the B's until you hit an A, then you circle all the A's, then a B. Okay, then you can count how many circles you have. So I have 1 circle here for B, then a second circle, third, fourth, fifth, sixth, 7. I have 7 runs, 7 above, below, median runs in this data. Okay. Now, if everything is happening randomly, you should see, you should see a reasonable number of runs because data will switch up and down a lot, right? But if you see too few runs, when would you see too few runs? So let me draw it here. Let's say your data is like this. So below, then you go up, then you stay up for a long time, then you come below. So you got 1 run below, another run up, another run below. You only got 3 runs. So this is suspect. This is sus. Okay, this is sus because the runs are too long and there are too few of them. You know, you're staying below too much and up too much. There's a pattern here. Okay. Another way to do this, to detect these runs and see if there's a pattern, is to go with up-down runs. So as long as the direction of change is the same, you keep it as a 1 run. So you look at change. So between observation 1 and observation 2, did you go up or down? We went up, so you write U. Between observation 2 and observation 3, did you go up or down? Well, 3 is higher, you went up, again U. Then 3 and 4. Between observations 3 to 4, did you go up or down? We actually went down because 4 is below 3, down. Then 4 to 5, did you go up or down? You went up. 5 to 6, you went down, right? So notice this. 1 to 2, you went up, that's this U. 2 to 3, you went up, that's this U I wrote right here. Then you went down, that's this D. Then you went up, that's this U. We went down, that's this D. Then we went up, that's from here. We went down, that's from here. We went up, that's from here. We went up, that's from here. We went down, that's from here. Now, you circle all the U's till you hit a D. So this is one circle. Then all the D's till you hit a U. Right after D, you have a U. That's another circle. Then a U, then a D, then a U, then a D, then a U, then a D. Then you can count. That's 1 run, 2, 3, 4, 5, 6, 7, 8. 8 runs. Again, you should be seeing, a reasonable number of runs. If you keep going up, 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 up like that, and then maybe you go down, 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 down like that. You got like what U, all the way till here. Then you start getting D, D, D here. So this is a long run going up, a long run going down. You only get 2 runs. That's too few runs. You have a lot of trends. So the up-down runs tries to capture trends. You have an upward trend, keep going up. Then you have a downward trend, you keep going down. It will detect trends. And the above, below, median runs, counting that detects whether you stay above the mean a lot, like a flat line above the mean, then you go down, you stay flat below the line, something like that. That's what it will capture. So counting these runs, we can capture patterns that can occur, and that can be because of special cause variation that you do not detect if you just compare the upper and lower control limits, because this is UCL and this line here is LCL, and you're within the control limits all the time. But there is special cause variation present. Well, not present here, these are fine, but if there were patterns, you can check that this is present or not. So how do we know how many runs are too much or too few? Well, after computing the number of runs, okay, you need to compute this z statistic, okay? R is the number of runs you counted. N is the number of samples. Each point on this graph corresponds to a sample. Why? Because if it's a X bar chart, this point is X bar 1. This point here is X bar 2, X bar 3. If this is a P chart, the first point here is P1, the P in sample 1. The second point is P2. Third point is P3, the proportion in sample 3, and so forth. So each point represents a sample. So N, the capital N, is the number of samples, which is number of points on your control chart. So here you can count that. How many points do we have? So let's change our color. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So our N is 11 here. Okay, so you'll plug N equals 11, and we had, for the above below median runs, we had 7 runs. So you'll plug 11 for N and 7 for R, and you'll solve this and see what Z do you get. Okay, if you're doing the second one, the up-down runs, then you'll use this formula for the up-down runs. R again will be the number of runs, which in this case was 8. Okay, and N will be the number of samples, which in this case was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so N will be 11. And this N is the same thing, that's also 11, right? And this N is the same thing as the N above, that's also 11. And you'll find the value of Z. Then you compare if the value of Z is too extreme, like +3 or more is extreme, less than -3 is extreme. So like -4 would be extreme, +3.2 would be extreme. So, outside +-3 z-score is extreme. Sometimes you want to compare with +-2. So that's like the 2 sigma, 3 sigma thing, right? For a 3 sigma level, you compare with +-3. For a 2 sigma level, you compare with +-2. So if the z is outside +-2 or outside +-3, the z values you computed here, then that indicates special cause variation is present, and you should investigate because you have patterns in your data. Okay, let's do a self-test. What do you see? In control process, no action needed. We did not count the patterns for the runs, but kind of looks okay. It doesn't look like up, up, up all the time, or just going up all the time like a trend. So it seems random enough, and it's within the control limits, so in control. This one is suspicious. Look at the below. This is below the mean, below the mean, below the mean, below the mean, below the, like the central line. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9 observations below the mean. Do you know what's the probability of getting 9 observations below the mean? Well, the probability of an observation being above and below is just a half, because there's a 50% chance you can be above or below. Getting 9 below in a row is a half times a half 9 times, or 1/2 raised to power 9. And let's call up our trusty Excel to see, what is 1/2 raised to power 9. So 1/2 raised to power 9 is 0.0019 or 0.002. Okay, so the probability is 0.002, or this is, in other words, a 0.2% chance that this could be observed without there being any special cause. So it's likely that this could have been caused by special cause. Along below mean run, investigate for special cause. When you get 5 or more below the mean in a row, or 5 or more above the mean in a row, that's kind of like, the probability is getting smaller. You can do 1/2 to the power 5 and see how small that is. When your probability gets, below, 1%, this probability, or below, 0.03%, like it did here, 0.002, you have a strong evidence for special cause. So, 5, 6, 7, 8, 9 run below the mean could be special cause. Okay, here we see out of control, just like, this is, this will, ideally you would do the z-test here, right, with the runs. And with the z-test, you would say it's out of control or not. So, you should have some more data, calculate the number of runs. Well, I guess here you would have 1, 2, 3, 4 runs. R will be 4, and N will be some value. You just count the number of black dots, and you can calculate the z-score and then really kind of compare, right? But you are going to say this is z-score is going to be probably extreme here, and you're going to say it's out of control, because your runs are kind of out of control. Okay, here you're just out of control, exceeds the control limit, right? So that's how you can read control charts. Now, control charts are not 100% sure. If a control chart says out of control, there's a tiny probability it was a false positive, which means the process was in control, but just random noise, or there's a small probability that you'll get an extreme sample. Okay, so we can think of it like this. What does the chart indicate? Are you in control or out of control? And what is the reality? That you can figure out by investigating in detail. If the chart says you're in control and the process is in reality in control, we are happy. Okay, everything's fine and dandy. If the chart says we're out of control and in reality we're out of control, maybe we're not so happy, but we're going to investigate and we are kind of like, okay, things are okay, things are working as they should. However, sometimes the chart will indicate that you're out of control while you are in control. That's called a false positive. The chart says red flag, things are out of control, and you go investigate and there's nothing there. That's called type 1 error or a false positive. Type 1 error, also called a false positive. And the probability is given by what sigma control chart you have. If z equals 3 and you have a 3 sigma control chart, the probability of a false positive is 0.3%. Okay, if you have z equals 2, it's a 2 sigma control chart, the probability of a false positive is a whopping 5%. And with a 4 sigma control chart is much lower than 0.3%. So there's very few false positives, right? Type 2 error means the chart indicates you're in control, but in reality you're out of control. If you choose a z that is too big, like you say, okay, I want to make 5 sigma control charts, my z will be 5. Okay, that's very, very broad control limits. Okay, you could be out of control but still not detected because you just want to avoid type 1 error, so you chose a huge value of z, and now it's very it will take a long time for you to go out of control. So you might still detect it eventually, but the process will be out of control for a long time, and it'll take a long time for it to exceed the limit. And by the time you detect it here, a lot of defects would have happened probably. So there's kind of like a trade-off, between type 1 and type 2 errors. All you need to know is, what is a type 1 error? It's a false positive. What's a type 2 error? Okay, it is a false negative. Control chart is saying negative, no problem, you're okay, it's in control, but actually you have a problem, right? So type 1, type 2 error, what they are, you should remember this table. Type 2 means control chart saying everything is okay, but things are not okay. Okay? And type 1 means control chart saying things are not okay, but actually things are okay. Okay? So you should know these. Now, we choose a trade-off between type 1 and type 2 error when we set the control limits. 3 sigma control chart limits reduce type 1 error to about 0.3% or 0.27%. Okay? However, risk of type 2 error may be significantly more. 2 sigma control limits reduces risk of type 2 error, but the risk of type 1 error is about 4.56 or about 5%. As a general rule, we prefer wider control limits when cost of stopping the process and searching for assignable cause is high. Imagine you have a continuous flow process. You are running an oil refinery. You are extremely rich. You control the oil supply to the whole world. Okay? And you don't want to stop the refinery for, when there's no problem. You don't want to because stopping and restarting the refinery takes hours, is a huge cost. Then you want to avoid type 1 error. You don't want false positives, to be stopping your factory again and again for no good reason, right? Because you investigate and you find no issue. So you want to have a large value of z. Maybe you're going to go for z equals 4 sigma control charts, so that when you're really, when you do stop, it's, almost always there was a problem. You don't have false positives. Okay. Highly capable processes have a large margin of safety before they will produce defects, and so control limits are often set at 3 sigma or sometimes 4 sigma for highly capable processes. Because if your capability is high, there's a long distance between the process output and the upper and lower spec. Notice the upper spec and the lower spec in the capability calculations are different than control limits. Do not mix upper spec and lower spec and control limits together. Upper spec, lower spec is what tolerance the customer is willing to accept. And that tolerance is for actual pieces of the product, not for a sample average. Whereas control limits apply to sample averages, and they have nothing to do with what the user is expecting. They have all to do with the inherent variation in the process. They're not looking at the customer. Okay, so they're different things. Don't mix them up. So for a highly capable process, the process is so far from the specs that even if it's a little bit out of control and it's kind of roaming around a little bit from the central target value, you're still not going to have defects because you're a highly capable process. If you have a highly capable process and you have a large cost to stop and investigate, like stopping an oil refinery, then you're going to choose a big value of 0 and avoid false positives. Right? If investigating for special cause is very cheap, you don't have to stop a lot of things. You can just go and examine things and know whether something bad is happening or not. Then you may use a Z of 2 or Z of 3. 3 is very standard, so it depends on your capability in the industry, but 3 is like a popular value of Z to use. Now for X bar R charts, when you do go to look up the A3 and the A2 or whatever, A3, D3, D4 values in that table, maybe I can show you, the table we had up here. Right here, right? So it does not say, this is from a textbook, it does not say whether this is a 3 sigma control chart numbers or not, but I believe these are 3 sigma control chart numbers. That's the most common, right? But you can get different numbers if you want to have a 4 sigma control chart or 2 sigma control chart. So for all of these charts, you can pick those values or the value of Z to control your risk of false positive. Okay, let's do an example, which is our X bar R chart. We have 5 samples. What is my sample size N? That is 4, because I have 4 observations per sample. I need to calculate the mean and the range for each sample. I need to calculate X bar 1, which is the mean of these 4 values, X bar 2, the mean of these 4 values, X bar 3, the mean of these 4 values, and so on down to X bar 5, which is the mean of these 4 values. And then for each sample, I want to calculate the range. So what's the range of sample 1? The highest value is 612. The lowest value is 588. 612 minus 588 will give me 24. So the range R1 is 24. So I'm going to calculate R2, R3, like that, right? And then you're going to find X bar bar and R bar, okay? So my X bar 1 is 601, R1 is 24, X bar 2 is 602, R2 is 10, and so on. I get for each sample, I compute my mean and range. Then I find the average of these averages, which is X bar bar 598, and I find an average of these 5 ranges, which is R bar, which is 22.4. Remember, my sample size N equals 4. So then I go and look at that table for the values of A2 and D3 and D4. The table I just showed you, okay, which is this table right here. So when N is 4, A2 is 0.729, D3 is 0, and that's 2.282, okay? Okay, so I look those up, right, and then I just plug and chug into the formulas, right? My D4 is 2.282, D3 is 0, R bar we just found on the previous slide right here, which is the average of the 5 ranges for the 5 samples, and then I get my upper and lower control limit for the R chart. Then for my X bar chart, I have to find X bar bar, which is the average of the 5 averages. Of these 5 averages, this is the average. That's X bar bar. And then R bar is the same R bar I put here, 22.4, the average of the 5 ranges. A2 comes from that table. Plug and chug, you get the upper and lower control limits. Okay. Now, part B of the question says, a new sample was obtained with the following readings. Are you in control? So for the new sample, you will compute X bar. This will be like X bar 6. It's a 6th sample, right? And so you'll do, 625 plus 592 plus 612 plus 635 divided by 4. You'll get your X bar 6. And then the range R6 for the 6th sample is going to be, what's the highest value? 635, lowest value 592. So you'll get 635 minus 592 which is 44. That's your range. So you'll plot the X bar 6 and R6 onto your control chart, okay? And you can see that the range of 44 is within the control limits, 0 to 51. And then whatever average you got, you'll see if it's within the control limit or not. Okay, so we got 43, sorry, is the range. 35 minus 92, that is 42, not 44. Okay. And the X bar is 616. So if you check here, well, X bar is outside the limits because my limits for X bar chart are 581 and 614. And my X bar 6 is sitting right here at 616. So it is out of control. So we should search for assignable cause variation, because in sample 6, which happened when a new employees were hired, something has happened. Maybe the employees are not trained well. So that is all for this lesson. So, you know, what did we cover? We covered process variation, common cause and special cause variation. Then we talked about process capability. If a process is capable, it makes sense to control it. To control the process, we can use X bar R chart or P charts or C charts, right? And when do we use each of them? That is all.